This is your practice quiz for chapter 3. We have 6 questions. We're going to do 2 videos. The first video is going to be the first 3 questions. And here we go. Question number 1, we've got a typo that I can see already. It says person A and B are pulling on an object on Earth at an archaeological dig. They're using ropes at an angle 30 degrees from the forward position. Person, there's a typo right there, should be person A pulls with a force of 70 newtons. Person B pulls with a force of 90 newtons. The force of friction on the stone is 100 newtons. What is the net force on the object, the magnitude, and the direction? So remember, force is a vector quantity. So here we go. We have this person A is pulling with a force of 70 newtons. Person B is pulling with a force of 90 newtons. So clearly, person B is pulling a little harder. The object is not going to go directly that way. It's going to go down a little bit because this guy's pulling a little harder. They're pulling at the same angle, but this one's pulling with more force. So it's clearly going to go down. So that's what makes this problem more difficult than if they were pulling with the same force, then it would just go straight. It would be a very easy problem. What we're going to have to do with this problem is separate everything into components, as we just love doing. So we're going to take person A, let's do it over here, person A, 30 degrees, pulling with a force of 70 newtons. We have an X component and a Y component. We're going to use sine and cosine, as we've always done, to find out the X and the Y components. And I'm just going to give you the answers to that. The X components using cosine turns out to be 60.62. The Y components using sine turns out to be 35. And if we want to use directions, we could say that this one is up, or sorry, that the X is to the right or east. And we can say that the Y is north or up. It doesn't really matter as long as you can express the answer at the end. That makes sense with the way the question is asked. Let's do person B. Person B is 30 degrees also, but pulling with 90 newtons of force, an X and a Y component, and you can probably see that the Y, you don't even need to do a calculation for the Y. When you've got a 30-degree angle here, this Y component always turns out to be half. You will learn that in 30-1. You'll see the relationships between 30 degrees, 60 degrees, called special triangles. And 45 degrees, they're special triangles. But I don't want to ruin the surprise, so we'll leave it right there. And then the X component turns out to be 77.94. So this person here is pulling with more force. It's going to be going down a little more than we would expect if they were pulling the same force. Now that we've got the X and Y components, we're going to add those. We're going to find the total X. And remember, when you're doing this, what makes this question more difficult is this force of friction here, right, is not an X or a Y component. It is both. Because if you're pulling in this direction here, then the force of friction is equal and opposite. Or not equal and opposite, sorry, it's opposite. That was a horribly unstraight line. It's in the opposite direction, so going this way. So it has the force of friction has an X and a Y component. So we can leave the force of friction, do that right at the end. First, we're going to find out what the total force of A and B is, and then we're going to take into account the force of friction. All right, so our total X is pretty easy. It's just 60.62 plus 77.94. They're both in the same direction. They're both going to the east or to the right. Add those up, and we're going to get a total of 138.56. Add our Y components. Total Y. And we have to acknowledge that those are in opposite directions. One's going up, one's going down, and so that's going to be 35 plus negative 45. That gives us negative 10. So there's our 10 going. It's going in that direction, whatever you want to designate that as being. Okay, now we've got the total x and total y. We can make a new triangle, and that will give us the resultant vector of A and B, not taking into account the force of friction. So we'll make a new triangle with our A and B values here, or sorry, horizontal, vertical. And that's going to be 138 this way, 138.56 horizontally. It's going to be 10 this way. Is our resultant vector R. The resultant angle is in there. And Pythagorean theorem, inverse tangent to get the magnitude of R and to get the angle of R. We do Pythagorean theorem, we end up getting 139 newtons for R, the resultant vector, and the angle turns out to be 4.1 degrees. Okay, so now we've got the angle, and we've got the direction. It's going to be going 4.1 degrees down, again, however you want to express that. And now we can take into account the friction. So the friction, let's go back to, is going to be going, that's 4.1 degrees there, so the friction is going to be going this way, it's going to be 4.1 degrees that way, it's 100 newtons, and since they're going along the same line, it's a one-dimensional vector problem, and all we have to do to find the net force on the object is to take the force of A and B and add the force of friction. Of course, the force of friction is going in the negative direction, so the answer becomes 39 newtons. And then our final answer to the question, 39 newtons, comma, 4.1 degrees. Now, this is going to be open to interpretation. And just because of the way the diagram is depicted, I'm just going to say 4.1 degrees below the horizontal. Below the horizontal. And that's only because the diagram and the question, they don't give any directions. And if I just look at the diagram, then it's right here. So it's 4.1 degrees below the horizontal. So that's an acceptable answer. If you want to designate an up, down, left, right, north, east, south, west, and then write your answer that way, that's also going to be acceptable as long as you say something like this is east, and then this is south. Therefore, it's 4 degrees south of east. Right? You can say that as long as you designate it somewhere in the question. The best answer, in truth, is right here for 39 newtons, 4 degrees below the horizontal. On to number 2. That took 8 minutes. A box of mass 5 kilograms moved on a smooth ice surface with a velocity of 6 meters per second. Right, a constant force is applied for 3 seconds, and the box reaches a final velocity of 12. What was the applied force? Okay, wow, this looks very much like a kinematics question, doesn't it? And it is. It's a kinematics and a dynamics question. We want to find out the applied force. So we're trying to find out the FA. Let's just write down what's given to us. Well, we're given the mass, which is a good thing. We're given the initial velocity, which is also a good thing. And we're giving we're given the time, 3 seconds, and we're given the final velocity. And be careful. Here's the crux, the most difficult part of this question, or the little quirk in it. It says 12 meters per second to the left. So if my initial velocity was 6 meters per second to the right, then my final velocity is going to be negative 12 meters per second. And that's where people are going to get caught up in this problem. All right, if I'm trying to find the applied force, what do I need? Well, here's my formula. And in this case, the F net and the applied force are the same thing. There's nothing else indicating a force of friction or any other forces. Therefore, the net force is the applied force. To get the applied force, I need the mass. I have it. I need the acceleration. I don't have it, but yes, kinematics right here. I have 3 variables, and I want to find the 4th. Back to unit 1. If I've got BI, T, BF, and I want to find A, I can use this formula here. BF is going to be negative 12 minus 6 divided by the time, which is 3 seconds, which would be negative 18 divided by 3. That's going to be negative 6. Negative 6 meters per second, which means the acceleration is in the opposite direction. And then I can just plug the, and let's remember here, I designated right as being positive, therefore it's accelerating to the left. I can plug that number in, I can put positive or negative, it doesn't really matter. I get 30 newtons, and what is the direction? What was the applied force? Clearly it was left. So there's the answer to that question. That one's pretty straightforward. It's got a couple little quirks you may want to be aware of. And then the third question here. Now this question is exactly the same one as we've done in our notes, but let's just go over it again. Just to solidify the ideas that are in this question. And it's a good question. It's a very good question. In fact, we've got a 20 kilogram sign. This is 20 kilograms. We want to know what the tension in cable 1 is and cable 2 is. Oh, another typo. Look at that. Of each cable. What is the tension in each of the cables? Okay. So first of all, we have to acknowledge that the sign is not accelerating up or down. So therefore, the net force, and I'm just going to put HOF, horizontal, equals 0. And the net force vertically equals 0. So let's start from there. The net force on both of them is 0. Actually, what we should have started, well, with a free body diagram. So let's do that next. This is step 0.5. And our free body diagram is going to look like this. We got T1 going that way. We've got T2 going completely horizontal. And what's the other force in this problem? It's obviously gravity, the force of gravity. So good free body diagram. We can see what our forces are going to be. And now we can build on this step 1, which says the net force horizontally and the net force vertically both equal 0. So in step 3, let's write down net force statements for each of those. So horizontally, what's our net force going to be? It is going to be, let's look at our free body diagram. Well, clearly, this is horizontal. So let's start there. Let's start with F net, which we know is 0, equals all of T2. All of T2 is horizontal. What's the other horizontal component? The other horizontal vector in this problem, and that would be the horizontal component of this, that's 40 degrees in there, of this vector here. So in other words, this one. And so we're going to designate that as being, T1, but the horizontal component of it, so we'll just put an X. X there. Okay, and remember, we know that F net is 0. Now at this point, we're kind of jammed up on the horizontal. So let's write a net force statement for the vertical. The vertical will be the same thing. The net force equals, so what's acting vertically here? Well, clearly gravity is vertical. All right, there. And what's the other vertical one? Yep, you guessed that it is the vertical component of T1. So this will be plus T1y. Okay, we've got our statements for both horizontal and the vertical components of the force or the tension in each cable. Now, where can we go from here? What do we know? As I said, in the horizontal one, we're kind of jammed up. We've got a 0 here. We don't know what T2 is, and we don't know what T1 X is, because if we take this triangle, is T1, 40 degrees, T1, X and a Y. We don't have any information to solve for X or Y. So horizontally, we're going to have to leave it. But vertically, that's the ticket. That's the key right here. Because vertically, yes, we have 0. What else do we have in the vertical components? We have FG. FG is always mg. So in this case, 20 kilograms times 9.81, which equals 196.2 newtons. So if we have Fg plus T1y, you can see right away we can calculate T1y. In other words, this y right here, we're going to be able to calculate that, and that is going to enable us to calculate everything else. So T1y equals, you can say, well, this should be negative actually, because that's going down. So it equals positive 196.2 newtons right here. And now you've got the missing piece of your right angle triangle, and you can use trigonometry to figure out what T1 is. So let's do that. If this is 196, we've got an angle here. 196.2 is opposite. T1 is the hypotenuse. So we're going to use the sine function to find out. So we're going to go, therefore, sine of 40 degrees equals 196.2 divided by T1. We can solve for T1. 196.2 divided by sine 40, and that's going to end up giving us 305 newtons. There's one of our answers. 305 newtons. To solve for T2, here it is. T2 is in the horizontal component, and we first need to solve for T1x. How can we do that? Well, again, we've got this triangle. We need to find this guy here, and we can use trigonometry to find that. Just to be safe, we're going to use, you can use cosine if you want, but let's use tangent. Let's just use tangent. The reason being, we'll do it down here. We're going to say that the tangent of 40 degrees equals the opposite, which is 196.2, divided by the adjacent, which is my T1x, the horizontal component right up here. And as I said, we could have used cosine. You could just use T1, but that would assume that this one's right. So let's do that, and that gives us T1x equals, turns out to be 233.8, 233.8 newtons. And now that we know that, we can go back up to here. T2 plus 233.8 newtons, and therefore T2 equals now T, in terms of signs, T2 and T1 are in opposite directions. It doesn't make a difference, really. It should be negative according to my calculation here. But we're just going to say it's 233.8 newtons to the right. And then if you want to be really specific, you'd have to go, this is 305 newtons, 40 degrees below the horizontal. Okay, but chances are the question is just going to ask for the, what is the tension in the cable? It'll probably just ask for the magnitude. So the answer to the question, what are the magnitudes? 305 newtons, 233.8 newtons. All right. Whoa, almost 20 minutes. Crazy. So next video will be the other 3 questions.